My self-described title is Internet Plumber at Google, which is to say I work with a variety of different teams within Google trying to figure out how we can make our products faster and also internet as a whole faster. And that spans kind of the full gamut. We have hardware projects, we have protocol level projects, which I'll talk about in a little bit, of things like SPDY, and also, of course, browsers. So I work very closely with the Chrome team, and as of late, I've been focusing on web standards. So I'm actually one of the co-chairs of the Web Performance Working Group, the W3C Working Group. One of the most interesting things that has happened recently in the space, in the web performance space, is actually the development of HTTP2. And of course, that's the topic for today. And the RFC has now been published, it's official, it's out, so I figured, we have an hour, and we can actually just do a group reading of the entire spec, right? I see a few cringe faces. It's only 90 pages. No, so we're not going to do that, right? That's something you can do on your own. What I wanted to do here is actually, we'll talk about kind of the primitives and specifics of what we are providing in HTTP2, but first I want to paint a picture of like, why do we have HTTP2, how did we arrive there, and what were the motivations? Because if you don't have the context, I think looking at HTTP2, you may be wondering like, why this particular set of features versus something else, and why didn't you fix my other favorite pet peeve in the protocol? So with that, I think a good place to start is actually right at the very beginning, right? Which is like HTTP 0.9. So this is what Tim Berners-Lee came up with in circa 1993. And he's a very pragmatic guy. You gotta give him a lot of credit. The protocol is incredibly simple. You connect to a host, you type in get, you type in the name of the resource you get, you hit enter, and you get back the resource, right? This is about as simple as it can get. That's a protocol. This is how HTTP begins. Now, it turns out this HTTP thing actually became quite popular. It started taking off, and there's a lot of organic adoption. So at this point, there's no formal process. There's no group that guides the development of HTTP. This is basically just somebody saying like, hey, this internet thing, it's kind of cool, it's taking off. I'm going to build a server. So if I'm building a server, I want to build a web page, and it'd be kind of cool if a web page had images embedded in it. Wouldn't that be crazy? So now that I have images and I'm not only transferring text, I need to do things like define a content type. So we started adding headers. And then somebody else comes along and says, well, delivering the same resource every single time is kind of wasteful, so why don't we add caching? And why don't we add these other features? So over time, we just start kind of grafting more and more features onto the protocol. And it's a very organic process. Like in a period of 2 or 3 years, there's just a very rapid evolution of all the different features. And HTTP 1.0 was not a standard. It was actually an informational RFC where the group sat down and said, okay, let's try and document everything that's been implemented so far. Like, let's take the common feature set across all these things and at least write it down such that if somebody else comes along and starts to implement this stuff or wants to implement this stuff, at least has a base of where to start. And that's HTTP 1.0. And here, the main difference is what I described is you have these headers, so you can actually describe some properties of the thing that you're sending. But still, one of the kind of performance problems with it is you connect, you specify what you want to get, you get the response, and the connection is closed. And at the time, this is still fine because we're fetching a page, right? Like it's a hypertext document. It's not hypermedia in that sense. So that's fine. Then a couple of years later, HTTP 1.1 comes out. And HTTP 1.1 was kind of the first coherent effort to rationalize the spec. So instead of just documenting everything, there's an effort to go through and kind of define terms, common terms, and explain the protocol in something that is actually like well documented and implementable, such that you can take the spec and if you write a server against that spec, you could expect the clients to actually work against it, at least the latest crop of clients. And effectively, that's what we've built the web on, right? This spec was published in 1999, and as we know it, there's been some updates, and actually in 2007, there was another effort to split up the RFC that became HTTP 1.1 and fix a bunch of other issues, which took another 7 years. So there was a set of new ones that were published in 2014, last year. But effectively, this was it, right? And over time, we just kept grafting more and more features onto it. Like, you can see that as I advance the slides, the text gets smaller and smaller because I need to put more and more headers, and this is just a subset, right? So in fact, if you do the analysis, you'll find that for every request and response, the average overhead of sending that today on the web is about 800 bytes. So we're sending 800 bytes of kind of this metadata in each request. And one of the gotchas with this protocol is we've allowed the responses to be compressed, but the metadata is not compressed. It's transferred as plain text, which was not a problem when we began, but turns out to be kind of an issue because here it's just a couple of headers, but we also added cookies, which allow you to store state, and cookies can be arbitrarily large. In fact, just the other day, I was looking at a website which dispatched over, when you load the page, it would dispatch over 300 requests, and those requests each would have quite a lot of cookies, and all of those would add up to over 1 megabyte of uncompressed metadata, right? This is not even the response data. So this stuff, it keeps growing. And the other thing, of course, that happened is when this spec was published, this is like circa GeoCities, right? And if you recall the web back in 1999, it is very, very different from the web that we know and use today, right? We got smartphones, we got tablets, we have all the multi-device capabilities, responsive design, and of course, access to sensors, hardware, like we're building applications. They're no longer web pages. And yet we're still building all of this stuff on kind of this old protocol. So in fact, if you look at the stats, like what is a median web page, if there is such a thing, right? There's a project called HPACK, which twice a month crawls the top 500,000 websites on the web. And it does not really care for the content, but it stores all of the metadata about the page. Things like how many requests were made, how many images were fetched, and other things. So if you query, I encourage you to actually take a look at it if you're not familiar with it. It's just hparchive.org. But when I ran the stats recently, you would find that a median page actually connects to 12 different hosts, distinct hosts. So effectively that says that when you open a web page, the client, the browser, has to connect to 12 different IP addresses. We end up fetching over 78 or roughly 80 requests to compose a page. So these are things like obviously the HTML, but also the CSS, the JavaScript, the images, and other things that you may have on your page. And all of that adds up to over a megabyte. And this number has been growing consistently. So if you actually just plot out the trends, you can see a pretty linear increase where you can basically extrapolate these numbers. And an average page, actually, I think these numbers are maybe 5 or 6 months old, so right now they're even higher. And because of all of this, the average page actually takes, the median time to load the page is 2.6 seconds, which may not seem like a lot, but it's actually quite a bit. And this number is specifically for desktop. If I try to load the same pages on mobile phones over a mobile network, which have their own unique properties that make them fast and slow at random times, you'll find that these numbers get inflated to 3 to 5 seconds, 3 to 7 seconds, or worse. And that's quite a bit of time. And we actually know that on mobile, in particular, this degrades very, very rapidly. So I don't think I'm the only one that has stared at a white screen on your mobile phone trying to load something, right? And I mean, we all know that's frustrating, and that's what we're trying to fix. So a good question to ask at this point is like, well, why does it take, say, 3 to 5 seconds to load one of these pages? So here's one example. This is a screenshot I took of yahoo.com. So if you're not familiar with this view, this is effectively what we call a waterfall, a network waterfall, where at the top you have the request for the HTML of the page, and then the waterfall are all the sub-resources that are declared in the page that we need to fetch. So as we're parsing the HTML, we've discovered that, oh, you're looking for the CSS file or this image, so let us dispatch the request. And you can see that this page actually, I had to clip it because it's actually quite long, but it ends up loading about 52 requests, and the whole page takes about 4 seconds to load. And 4 seconds is quite a bit of time. And this is yahoo.com, right? They've actually done a really, really good job of optimizing the site. And one question is like, well, come on, right? Like with all of the engineering know-how and all the rest, couldn't we do better? And then there's another interesting bit that you might not see unless you do kind of deeper analysis, which is, why does it take 4 seconds, right? This page is actually not that large in terms of total number of bytes. And in particular, if you look at the bandwidth consumption chart, as the browser is trying to create this page or render this page, you can see that in this case, we actually have a fairly fast connection. We've capped it at about 4 megabits per second. And we're trying to load this page with 52 resources, and the bandwidth is barely utilized, right? So it's like, well, what the heck is going on? If I gave you a 10 megabit connection, shouldn't you be able to give me a much faster page load? And another view that I think explains this problem even better is to look at the connection use. So this is the exact same page, but instead of focusing on per request level, we're actually looking at the actual connections. So this tells you that yahoo.com actually opens 30 TCP connections to fetch all the resources. And the thing to notice here is actually that it's mostly blank, right? There's a lot of empty, dead space. And what happens here is we make the request at the beginning, and we start receiving HTML bytes. So the blue bar is the actual download time. This is us receiving useful response back from the server. And as soon as we start processing this response, we start making other connections. So these little bars actually indicate the different phases of the connection. Things like I did a DNS lookup versus a TCP handshake, or I've sent the HTTP GET, right? So this is actually this phase right here. And then if you look at this kind of chart here, you see this like big space in between. So what's happening there? Well, it turns out that's just the latency. That's just the latency of me sending a request to the server, and given the RTT to the server, I have to wait for a certain amount of time before I get back the response, right? And in fact, the blank space here just illustrates that latency is really the underlying problem. So we can't make use of all the bandwidth because the latency is really the limiting factor. And that is one of the kind of fundamental challenges for us to design web pages. And this actually led to an interesting, at the time, discovery and motivation for why we started working on SPDY within Google. So as the Chrome team, which was founded in around kind of 2007, 2008, started building the browser, we discovered that we were running into this problem when we were doing the analysis, trying to figure out like, how do we make the browser faster? And the team actually did this experiment where we took the top 100 sites, and we ran a simple experiment saying, like, what would happen if I fix everything, and then I start with 1 megabit downlink, and then I double that to a 2 megabit downlink, and a 3 and 4 and 5. Like, what would change? Is it bandwidth that's limiting us, or is it latency or other things? So the results of the experiment were pretty interesting. If you start with a 1 megabit connection and you double your speed to a 2 megabits, the performance roughly doubles, which is great news, right? It means that you were bandwidth limited. Then you go to 3 megabits, and all of a sudden you're like, wait, that didn't quite get me as far, right? And by the time you get to 5 megabits, we actually found that you're basically getting single-digit performance improvement, which is kind of interesting because we know that the average connection speed, let's say in the United States, is actually over 5 megabits per second. So if you're at home and you're thinking like, hey, I'd really like to improve the performance of like browsing the web, I'll just get a faster connection from Comcast or whoever else, your browsing is not going to get significantly faster. And that's quite sad, right? Like you can stream HD movies or movies in general, large streams are bandwidth bound, and getting a faster connection will help there, so you can upgrade from a regular definition movie to an HD movie, but your browsing is not going to get any better. And that's a fundamental problem. But then we did the same experiment. We just started playing with latency. So we had a fixed link, and we just started kind of ratcheting the latency up and down. And we saw a very linear relationship between latency and the actual performance on the page. So the conclusion was that latency is, in fact, the #1 problem for us in terms of the browser and loading web pages on the web. So if we want to make the web browsing faster, we need to focus on improving latency. And that's kind of challenging, because if you know how latency works, right? Unfortunately, we have the speed of light, and we have not figured out how to fix that yet. And the current links are actually within like a constant factor of the maximum speed, right? Like, yes, we can go from 1.5 times the speed of light to 1.3, but that's not going to be substantial difference, right? Like, we'll get 30% improvement. So what do we do about that? Well, basically, the realization here is that HTTP data flow, specifically for browsers, because we compose our web pages of many small resources, which are coming from many different sites. They are mostly small resources, and they're very bursty. Whereas TCP, the transport itself, is optimized for big transfers, right? That's where TCP really shines. So if you're watching, once again, a video stream or a HD movie, this stuff works great, but latency is a problem for HTTP in terms of web browsing. So of course, we're web developers, we're smart. When there's a will, there's a way. So we start coming up with kind of workarounds and hacks, and we call them best practices and optimizations. So one such example is parallel downloads. So HTTP1, the protocol itself, does not allow the server to respond with multiple responses simultaneously. It's a serialized protocol. I need to send the request, I need to get the response, and then I can issue the second request. In theory, there was an extension proposed, which is pipelining, but in practice, it was never deployed because of broken servers and other things. So for all intents and purposes, I have to send the request, I have to wait for the response, and only then can I send the request. So effectively, your parallelism is limited by the number of connections that your client will open. And after kind of a lot of wiggling back and forth, all of the browsers converged on this kind of interesting behavior of opening up to 6 connections per origin, where origin is defined as the host and the port number. Right? So if let's say in this example, I have a web page, photo gallery that tries to load 12 JPEGs, or just like 12 tiles on the page, you will see something like this in your waterfall. The first 6 requests will go out immediately. Each one of those requests will, under the hood, open a new TCP connection. That's how we're getting parallelism. But then because we only allow 6 requests per origin, the other 6 will actually block. And that's what this opaque or semi-transparent bar shows here. It's like, we know that we need to send this thing, but we cannot because we're waiting for a connection. And then as soon as one of these things come back, we dispatch the next request. So you kind of have this stepladder pattern. And that's why we have the waterfall, right? So that kind of sucks. There's other concerns with opening many TCP connections. Say you have a TLS connection, that means more handshakes. That means more overhead for the server because each connection requires state. So there's just inherently a lot of overhead. And that kind of sucks. And it also actually affects TCP performance because TCP was designed to optimize your flow, but it can't optimize the flow in the same way when you have multiple connections going against the same host, right? Like it does not know about the other connections. So they all compete with each other, which is obviously suboptimal. So, we're developers, we're smart. We actually say, well, 6 connections per origin, no problem. I'll just have 2 origins, right? I'll have 1.myawesomeapp.com and 2.myawesomeapp.com, and then you'll open 12 connections. Isn't that great? I'm so smart. And if I need to load 30, I'll just have 5 origins. And that's exactly what we did in the web performance world. We just said, we're just going to shard our assets across many different domains. And that worked, at least in theory. And then you start digging into, like, so what are the implications of doing that? And this is an example from Etsy.com. So Etsy, this is their search page. You search for, I don't know, awesome bag, right? And they come back with a listing of many different bags that you can buy with photos. And they sharded, I think they have five different shards at the time. So the browser would open up to 30 different connections. And you don't see the sort of data when you look at your network waterfall in your browser. But if you look at the TCP dump and you look at the retransmission rate, right, where if the network gets congested and packets get lost, the server will retransmit after a certain timeout the data that it needs to send. And what you see here, the spike over here, is the retransmission rate. So at first, the Etsy server is sending a lot of data and it's being received by the client. Then the link gets congested, packets are getting dropped on the floor, and they're being retransmitted. And it turns out that actually in this case, they're being retransmitted twice. So the original packets actually eventually make it to the client, but then you get a duplicate. So you're actually transferring significantly more data to the client. You've almost doubled, in this case, the amount of data you had to transfer because of the TCP retransmission algorithm, which is obviously not great, right? And if you think about use cases like emerging markets, where data is incredibly expensive still and will continue to be, this is a huge, huge problem. So what's the magic optimal number of shards? There's no such thing, right? Because it totally depends on your connection or on your environment and your connection between the client and server. If you have a very low latency connection with lots of bandwidth, sure, open as many connections as you want. If you're on a shaky connection at the moment, maybe it's a Wi-Fi with lots of people on it, you actually want fewer connections because you don't want to overwhelm the client. So in the web performance world, we kind of just put this under the rug and ignored it for most of the time, but it's an issue. Next, us web developers said, hey, we can't fetch many things in parallel. We're clever, so we'll just combine things together, right? Instead of fetching 3 JavaScript files, we'll just put all of the 3 files into one file and just fetch that one. That fixes the problem. Turns out that works, and that's actually a reasonably good best practice, if you will, because it fixes this whole parallelism issue, so you don't get that stepladder. And sometimes that actually improves compression, because if you have 3 things that are very similar, you can compress them and get better savings, right? So that's good. But turns out it actually has negative repercussions as well. One of which is if you put many files together and then you update a single byte in any one of those files, you have to refetch the entire bundle, right? Which is very, very bad. So I know of many popular frameworks that will take very stable code, like they'll take jQuery, which is a very popular kind of basically static thing that you never touch as a developer, which is 30 to 50 kilobytes, and they'll bundle it alongside all of their code. And then every time they twiddle one bit in their code, you have to refetch the entire jQuery file, which kind of sucks, right? And for many web apps on the web today, these things are getting updated like many times a day. We're deploying constantly, so users are forced to refetch this stuff. So caching is effectively broken. Like, it works, but it does not work as well as it should. The other issue with this stuff is for certain types of assets that the browser receives, we cannot process them until we have the entire file. So it turns out that if you send us smaller chunks, we can get the chunk, start processing it, and then work on the next one, as opposed to waiting for the entire thing and then starting to execute it. So CSS and JavaScript is such an example. So, okay, this is not great. We break caching and we break some of the processing. Another optimization that we came up with was inlining, which is to say, hey, you requested index.html. I have this, let's say, an icon or a photo that I know you will need on this page. So instead of you asking me for it, I'm just going to embed it. So I'll just base64 encode it and just stick it into my HTML page. And that works because it also reduces the number of requests. But now that asset has become part of the page. So if that asset is shared between multiple pages, you have to duplicate it on every single page because you're literally inlining that content into each page. It also breaks some of the prioritization primitives. And it messes with caching once again, because say you've embedded that asset across many different pages. The moment you update that one asset, you have to invalidate all of these other pages. So not great. And then finally, prioritization. So one of the things that we realized as browser makers, if you will, that over time, as developers started building more and more complex and ambitious web applications, there was a larger burden on us to make sure that we're loading assets in the most optimal order to make sure that the page comes up as quickly as possible. So we started embedding a lot of heuristics into the browsers for how do we fetch these things in optimal order. And to be honest, there is no one answer to this. So we take a lot of guessing. Like, effectively, we play this game where we say, OK, we have 6 connections. We got 40 resources, some of which are still being parsed and we don't really know about. So what do? We know we have 4 critical resources and we have 2 that are not so critical. Should we wait to parse some stuff more? Because if we discover a critical resource, then we should put that ahead of the sub of something that's still lower priority. Or should we dispatch it as quickly as possible? And we keep changing these algorithms because we find as the web evolves, as web speeds change, we keep having to twiddle with this. But this actually hurts web developers because you, as somebody who's performance conscious and monitors their website, one day the site loads this fast, the other day the site loads this fast because we keep kind of changing the strategy. And it's clearly suboptimal. So for example, in Chrome, for a while, and I guess we still do, we limit the number of images you can download because we want to reserve some connections for critical content. So if you put a JavaScript file or CSS style sheet at the bottom, which is critical for us to get the page visible, we want to keep a connection available such that we can dispatch that as quickly as possible. So if you're building a photo gallery, that's the bane of your existence because you have no say in that sort of prioritization scheme. And unfortunately, HTTP, the protocol, has no notion of priority. And that's yet another problem. So kind of to recap, it's a serialized protocol, right? Request response. We have this issue with limited parallelism. Basically, you have the number of connections that you have open is your parallelism. You can work around this via various hacks, or we call them best practices and optimizations. But it's just not a great outcome. And also, there's client-side delays in the sense that the browsers have been forced to queue things. So even though we know that we need to request something, we will delay it until such time that we think is better because we're not sure what's going to happen next. And we briefly talked about the overhead, but this turns out to be actually quite a big problem for many people, where there's just a lot of extra headers and cookies that are being sent on each request, which just adds to the overall bloat. So if you're trying to build a high-performance RPC protocol, that overhead adds up, and it adds up very quickly, right? Yeah, we're talking difference of like 100, or several orders of magnitude between something that you can craft yourself that is adding a couple of bytes of overhead versus 800 bytes. So all of that is the kind of to build up the motivation for what is HP2, why did we come to it, and what are we trying to solve with it. And if you look at the intent, or when we first started HP2, there was a discussion about like what is a charter? What are we trying to address in HTTP? Because HTTP is such a successful protocol that fiddling with its bits is, it's very dangerous. We want to make sure that we do the minimal amount that will give us the most payoff and kind of leave the rest to later. So we crafted the charter to say, well, we're going to focus on latency, and we want to improve latency in terms of loading web pages, knowing that all the kind of issues that I described before. We want to fix the head of line blocking, so you don't have to do this request, wait for a response. We want to collapse the many connections into one, because we know that helps both the transport and the efficiency of the protocol itself. And further, we will not change the semantics of HTTP 1.1. So all of the verbs, the headers, the set cookies, and all the rest, that all works. We're not going to touch that. So we're only going to concern ourselves with kind of lower layers. And I think this is important because one of the criticism of HTTP2 has been like, well, why didn't you fix cookies and other things? And why didn't you add more headers for my particular use case? And the answer is that specifically outside of the scope of the charter. That's not to say that those are bad ideas or we shouldn't do them. We will, but the intent was to fix this particular set of problems. Just because we want to actually ship something as opposed to bike shed it for 2 decades and not have it deployed. So the brief history of HTTP2 was that originally, back in 2007, 2008, when I showed you that experiment with bandwidth and latency on the Chrome team, we actually, when we saw that result, we started working on a protocol called SPDY, which is an experimental protocol that eventually became the foundation for HTTP2. And here I'm showing you an adoption chart of SPDY as a protocol. And you can see the main takeaway here is that virtually all browsers saw benefit in it once we started deploying it. So Google Chrome and Google servers were the first ones to experiment with it. We showed that there was significant improvement. Firefox and other browsers started to adopt it, and at that point, the HTTP working group said, like, hold on, right? Like, there's something here. We should sit down and figure out how we should standardize this, because at this point, it was just like Google was developing this as an experimental protocol. So after doing a call for proposals, SPDY was adopted as a base, and then since then, they went to do kind of many iterations to define what is HTTP2. So as of today, SPDY still exists. It's still supported by all these browsers, but we've announced that, for example, Chrome will deprecate SPDY starting in 2016, so at the beginning of next year. So we want to make sure that everybody migrates toward HTTP2. But one way to think about SPDY is the experimental branch of HTTP2. As we were writing the spec for HTTP2 draft, we were implementing features in SPDY just to test, like, does this stuff work? Right? And we would implement it on our Google servers, the Twitter servers, Facebook, and lots of other sites. So if you look at a similar adoption graph for HTTP2, you'll actually find that the support is actually building really, really fast. Given that the official RFC was published back in May, this is pretty amazing, right? You already have, so IE, which is IE 11, and Edge, which is coming out at the end of this month with the new Windows version, supports HTTP2, Firefox, Chrome, Safari. So Apple announced that they will support it in their core networking stack, which means that Safari will support it in all of your iOS apps. Similarly, Android's looking at it. So there is sufficient momentum behind the protocol. And that's to say that HTTP2 is here. Like, this is not something that was written in an ivory tower or some working group with no experience. This was deployed, this was tested with SPDY, or through SPDY, I should say, and it's replacing SPDY. So it's here, it's already running. If you're using Google Chrome and you're talking to, say, a Google server or Facebook server, you're actually using HTTP2 under the hood. And here's some interesting stats. So back in February, Firefox enabled HTTP2 as, enabled it by default in Firefox. And you can see Patrick here, who works on their networking stack, that they're actually, shortly after they enabled it, given kind of the widespread adoption of this protocol, they were already seeing more HTTP connections than SPDY. So that tells you that it's already being widely deployed. And looking at our own stats from within Chrome from about a month ago, I can see that when you connect with TLS to some server, roughly 45% of those connections negotiate HTTP2 today already. So there is significant adoption across the web. And that 28% is using the old kind of SPDY version. And if you're wondering why there's actually HTTP1 that's using ALPN, that's because that's a performance optimization that allows the server to do a one round trip handshake. Okay. Whew. HTTP2 in one slide. So we'll talk about all of these in a little bit more detail. But at a very high level, there's only one TCP connection. So our goal was, if you have an origin, we should only need one TCP connection. You may still have multiple origins that you fetch things for your site. Nothing we can do about that. But if you have a connection to an origin, there should only be one. In kind of the parlance of HTTP2, a request is mapped to a stream. So whenever you hear me say stream, just think of it as a request. And streams are broken up into many different frames, which allows them to be multiplexed and interleaved, the frames of the different streams. And then because of that, we also have a number of new primitives, like we can prioritize frames, we can flow control them and do other things. And then we also have header compression, which finally allows us to compress the metadata such that we don't have to transfer the same data over and over again in plain text. So once again, this is, I think, a very important point to stress. We're not replacing HTTP. All of the things that you're kind of familiar with, like get this, header this, and all that all stays. Any application that you have today that's running over HTTP 1.1 or 1.0, you can put it on HTTP server. It'll work just fine. There's absolutely nothing you have to change. But there are things you can change that will improve its performance, right? Because you can start undoing some of the things you were doing before, like, for example, sharding or concatenating files, because there's no longer this constraint, and get better caching or better performance out of the protocol. So it's a pretty kind of gentle upgrade path, if you will, right? Like it's a take it and apply cautiously. So at the base of this whole protocol is the binary framing layer. And I know people have different reactions to that. There are people that really love the text protocol, and where you can telnet and you type in get and you specify the path and you hit enter and you get something back. With a binary protocol, obviously you cannot do that, but there are many other benefits to a binary protocol. Performance is one. Right? We know that we're pushing a lot of traffic through HTTP, so it's actually more performant to implement a binary protocol. It's also more provably correct. If you ever try to implement the HTTP1 standard, you'll find that there are many different ways to delimit headers and know when there's end of the response, which is very hard to process. With binary protocols such as this one, it's very simple because all frames have a consistent header that say, what is the length of the frame you're going to be parsing, what is the type of the frame, and some well-defined flags, right? So if you only care about a particular frame, you read the first byte, you say, or the first couple of bytes, and you say, okay, it's going to be 50 bytes. It's a type of header that I care about, so let me read it, or let me just skip over the stream. So that becomes much more efficient. And the standard itself actually defines 10 different frames. These are the ones here. So settings is something that you would exchange at the beginning or sometime during the connection to negotiate change settings of the connection, right? Like maybe you want to limit the number of streams that can be open or lower some other thing. Headers is exactly what it sounds like. Continuation is an extension to headers. So if headers, for some reason, do not fit in one block, you have to send a continuation frame, which contains the rest of the headers. Data is exactly what it sounds like. Priority allows us to reassign priorities. So I could have sent you a request saying, hey, this image is very, very important to me. And then the user scrolls away from the page, and that image is no longer important. You can send a priority frame saying, like, yeah, still important, as in I want to get it, but not as important as this other image that I'm fetching now because it's in the viewport of the user. So that's really nice. We finally have ability to reset a stream, which is to say cancel a stream. This was not possible with HTTP1. The only way to cancel a fetch with HTTP1 is to close the connection, which is terrible, right? Because you have to incur the TCP handshake and all this other stuff. Here you can just say, no, I no longer want this for whatever reason. We have things, we have push promise, and I'll talk about this. This allows the server to actually push data to you. So you can ask for a thing, and the server can say, okay, here's the response, and by the way, here's the other 5 things that you will need, which is kind of cool. Window update is used for flow control. We'll talk about that too. Ping is exactly what it sounds like. It's more of a diagnostics frame that you can use and check for liveness of the connection. And go away is a way for either the client or server to signal that they want to close the connection. And this is an interesting feature because with HTTP 1.1, you never knew if one of the sides finished processing the request. So say you sent a request, like a post request saying, I want to log out of your thing. And then you close the connection. Did the server really get the request? Go away allows us to actually acknowledge that and say, I'm sending you a go away frame, and I'm closing the connection. You will get that thing, and you will know exactly how far I've processed the stream, because everything after that I would have safely ignored, which is another nice feature that was missing. So another nice property of the spec, if you're familiar with RFCs and ATS specs, you get lots of ASCII art. This is one of the more beautiful examples. Every stream has a very well-defined lifecycle. So these are effectively states of each stream. So every stream or request starts in the idle state. Then you can send this in the middle, you can send a headers frame, at which point a stream becomes open. And then you can send a reset stream to close the stream. And basically this documents exactly the full flow of all the possible permutations of where and how the stream can get there, which is incredibly useful because if you ever try to implement HTTP 1.1, you'll know that this is a very, very hard mess to untangle. And this makes it very, very simple. So there are well-defined semantics for what constitutes a protocol error, what constitutes a connection error, at which point you have to abandon all work, and other things. So as somebody who has actually implemented the spec, I can tell you that implementing HTTP 2 is actually significantly easier just because of this and kind of having this data. So to recap, the difference between HTTP 1 and HTTP 2 is that in HTTP 2, we take the headers and all the metadata that you want to send, and we break it up into frames. So this allows us to have one connection, and because we have these different frames, we can now interleave them. We can actually say, here's a data frame, here's a chunk of the data for the previous response, here are the headers for the other response that I'm already processing. And you can interleave these things, and obviously this is bidirectional. So this is an interesting metric from Patrick McManus. We had a different quote from him earlier. This is once again coming from Firefox, and the important part is here. So he's saying that for HTTP 1, 74% of connections carried a single transaction. With HTTP 2, because we don't have to do multiple connections to get parallelism, that number plummets to 25%. So that tells you that we're getting much, much better connection reuse, which you're familiar with TCP also means that we can grow our congestion windows larger, we get better retransmits because we have larger windows and all that stuff. So even from an operational standpoint, this is a huge win because if you're running a huge server farm, your number of connections just collapse by a significant amount, right? Which propagates all the way down through the stack, and that's a great win. So we know that this stuff is actually working. I hinted at this a few times now. Prioritization is incredibly important. I talked about kind of different conceptual priorities for things like CSS, JavaScript, and images. In HTTP 2, we actually have a protocol primitive to express that. And specifically, we provide two mechanisms. One is you have streams, right? And streams can have a weight, and they can have a dependency, which is another stream. So if you have two streams that are leaves of the same node, you can assign weights to them, which basically tell us how much bandwidth we should allocate to each one. So you could say, well, this image is not as critical, so if you're under constraints, if you're under bandwidth constraints, like trickle the bytes to me because maybe I want to show a progressive scan of the image as it's loading, but dedicate most of your bandwidth to the critical resource like CSS or JavaScript. Or you can go one step further and actually say, well, you know what? If possible, please deliver this first file before sending me the second file, right? And this is not strict in the sense that it will force serialization on the server, but it's a explicit hint to the server, because say you can't make progress, the server can't make progress on D, say it's blocked on the database, but it has the data for C. There's absolutely no reason that the server should block, right? That would in fact reintroduce the whole head-of-line blocking issue. So the server is allowed to send data for C, but it should allocate preference, like as soon as D becomes available, it should start pumping bytes from D. So this allows us, the client, to communicate the entire dependency graph or the priority tree for all the resources as we parse it to the server. So we don't no longer have to play these heuristic games in a client trying to guess like what's coming next, right? Or we can just say, we know that this file is very important, send it to the server, and then if that changes, we can actually send a priority frame to lower its priority. And of course, I keep discussing all of this kind of in the context of a browser because that's a context that I'm most familiar with, but HTTP is used outside of the browser as well, right? It underpins a lot of our API traffic and many other use cases. So this is also useful in those contexts as well. So with HTTP2, and I guess I already said this, say you have an index file, instead of deferring something and waiting, we can send all the requests immediately. We no longer have that step ladder. We just push all the stuff to the server, and we rely on the server to do the right thing, which is it should respect those weights and respect those priorities. And here's actually an example in Firefox. So they've implemented this strategy where they have several different groups. So they have things like leaders, unblocked, and background. So think of these as kind of conceptual buckets where they say there are certain types of requests that the browser makes, that the application makes, that are considered to be background requests, like analytics requests. Those things are very important to the application, but they're not critical to get the page visible. So if we're under contention, we will defer those until later. So that's why the background request has a very low weight, right? It has a weight of 1. Whereas something like leaders, which is JavaScript and CSS, which is in many ways, like you need the CSS for us to paint something to the screen, and we need the JavaScript to actually construct the darn thing, the contents of the page. That is very important, so give it the highest weight. And then there's stuff in between, like XML HTTP requests and other things. And things like images should come after JavaScript and CSS, because we can't even show the image until we know what the page layout is. Right? So this is kind of like, this is a fairly simple strategy for how to prioritize things, but this is what's implemented in Firefox today. It'll categorize resources into one of these buckets, and it'll communicate that down to the server. Another interesting feature that we've now added into HTTP2 is we have many different streams flowing along the same TCP connection. And it's useful to be able to say, it's useful to be able to rate control on a per stream basis. So one example of this is a proxy, which may have kind of a different, your downstream may be very fast, your upstream may be very slow, and you don't want to build up a huge buffer in the middle, right? So you want to rate limit the server to say, like, stop sending me data, right? Like, I need to clear the buffer and send it to the client. So that's useful for proxies, but it's also useful for the browser because now we can actually do some pretty interesting things, like do smarter image rendering. For example, say you request an image, a product photo or something, right? There are certain image formats that allow us to render progressively. That as the more data we have, the finer resolution you get the image. So instead of fetching the entire thing and delay that until later and declare that low priority, what if we could say, give me the first 20 kilobytes of data, because that is sufficient for me to decode the dimensions of the image such that I can do the layout of the page, and it also is sufficient for me to render a low-res preview, which is not going to be terribly pretty, but it's like it's something, right? It allows the user to start seeing kind of the pattern of what you're trying to show. And then I will pause that until such time that all the other critical resources have loaded, at which time I will resume the stream. And the way this works is you request the product photo, and during the initial negotiation, you can actually declare what is the starting window for each stream. You can declare that window to be, say, 20 kilobytes. And then you have to manually update it. The client has to update that window by sending a window update. So it's a very basic, very simple scheme, right? Every time the one end sends data, it decrements its window size, and the other end has to send a window update saying incremented by this amount. Right? So very simple. You can implement any sort of strategy that you want with the sort of mechanism. But it allows us to start doing fairly interesting and sophisticated things, for example, within the browser. And I'm sure you can imagine other examples as well. So to some degree, yes, we're absolutely re-implementing TCP flow control, but that's because we're bundling other streams within TCP that TCP has no knowledge of, right? And such is life, I guess. Server push, I mentioned a few times, so this is kind of interesting. In HTTP 1 world, there is a one-to-one correlation between a request and response. You send me a request, I give you back a response. But we know that developers often or frequently want to send multiple things in response. So if you think about it, inlining a resource into another resource is one such example where you say, well, I know you're going to need this, so I'm just going to embed it into the other thing so it's such that you don't have to round trip back to me to get that same thing. So what if we actually allowed that as a primitive within the protocol where the server can say, oh, you're asking for this? Sure, here's the response, and I also promise to deliver you these other 3 things that I know you will need anyway. And that's what server push is. To do that, you actually send a push promise. So this is a different frame that basically says, here's the response, that's the data frame, and here's a push promise that describes the resource that you're going to push. So if you're requesting my index.html, I can also push you the CSS file and push you the JavaScript file and maybe some other things, which is kind of cool, and it's an obvious latency optimization. It's also useful for other examples like API traffic, right? Say you request one thing and the server responds with a bunch of things back at you, which is quite nice actually. So it has actually many different benefits. It allows you to deliver granular resources. So pushed resources are just like any other response. They can be cached, they can be reused, they can be prioritized. So all of the nice things that you get out of making the request, you basically get with push as well. And there are mechanisms for the client to control how server push is used. So if you really don't want to use it, say you're on a very expensive connection, you're roaming and you're very cautious about the data that you fetch, you can actually disable server push on the client to say like, you know, I'm willing to accept the extra latency of making that request and that round trip because I don't want you to speculatively push things that I may not need, which is nice. So that mechanism is there. And kind of one cool example of this is automation. So this opens up new venues for servers to become much more smarter. So instead of us, the developers, having to determine like which resources need to be inline or concatenated, one example is Jetty, which is a Java implementation. What they do is you boot up the server and people just start hitting the server. Nothing is happening. And what they do is they observe what happens after they send back the response. So they see that you came for the index file, but then you immediately came back and asked for the CSS and JavaScript file. So over time, after a couple hundred hits or something, they build up this map saying like, look, with very high confidence that if you ask for the index file, you're going to come back to me for the CSS and JavaScript. So in the next hit, why don't I just push it to you? Right? And all of a sudden, you have this runtime optimization that can adapt to the particular clients. It can be changed on the fly. And as developers, we no longer have to kind of burden ourselves with this sort of thing. Which, if you think about it, like our compilers do this, right? We find a hotspot and we optimize it. This is a similar type of thing in a different context, which I think is really cool. And I think I've hinted this any number of times now, but with HTTP2, the client relinquishes a lot of control by providing a lot more data to the server and just pushing it to the server. And we're saying like, look, I need this many resources. Here's the dependency graph between them, like X before Y, and these resources have this sort of ordering. And the server needs to be aware of such things. So if, hypothetically speaking, you were like so enthusiastic and hyped up about HTTP2 after this talk that you went and read the spec and started implementing the binary protocol, you could probably implement the framing layer pretty quickly, right? And you have a HTTP2 server up and running. You're like, there, I'm done. Congratulations, right? I can parse and emit these frames. But unless you implement the prioritization correctly, and that's probably the harder part, the much harder part, you may actually hurt performance because previously the client did a lot of tricks to kind of synthesize prioritization, whereas now we're just dumping it all to the server and rely on the server. And that is the only way we can get the latency win and the performance win, but at the same time, we are at the mercy of the server. So if you're deploying this stuff, please do your due diligence for like making sure that your server supports these sorts of things. Because I've seen benchmarks where people do implement kind of that toy server, and they run the benchmark, and they're like, hey, this HTTP2 thing, it's not as fast as it seems. It's like, well, yeah, you need to implement these other primitives for the stuff to work. I didn't talk about this much, but I hinted at the problem with headers. So HPACK is actually a separate RFC that was published alongside the HTTP2 RFC. It's used by HTTP2, but it can be used in other contexts. So HPACK is a compression mechanism for headers. And you may wonder, like, why did we have to reinvent a new compression algorithm for headers, right? We have plenty of compression algorithms. And in fact, in SPDY, we actually started with just using gzip. But later, after about a year, we discovered a couple of security problems with using gzip. So the reason, and if you're interested in this sort of thing, you can, I can point you to other resources that will explain this. We had to implement HPACK that addresses that. So HPACK actually has two mechanisms. One is just basic Huffman coding. There's a static dictionary that's specified in the spec. That static dictionary is used to compress strings before they hit the wire. And then there is an index table. So the way this works is, let's say you have a request. A request consists of key value pairs. It's the header name and the value, right? And we want to transmit those. So in order to transmit those, we have each side of the connection keeps what we call a static table and a dynamic table. Static table is defined in the spec itself, and the dynamic table is something that gets filled up as the connection progresses. So I take my collection of key value pairs and I run them through this static table. And for example, you take something like method get, right? It turns out that the static table already defines method get because it's a very common thing to send, right? And you know that it's index 2. So the only thing you have to send is 2. You just say like 2, and we know that on the other end that's a method get. We can decode that. For things that that are unique to your site, we will use Huffman coding, and then we will place them into the dynamic table. So now this becomes entry number, say 19 in the dynamic table. And in the future, if you re-request the same path, we will just send 19, right? So this allows us to achieve much, much better compression. Because if you look at things like user agent headers, which is this very long, opaque, seemingly random string that says, I'm kind of like Mozilla, which is kind of like IE, which is like Gecko, which is like Firefox, which is like Safari. It makes no sense, right? But it's static, it does not change. So we don't have to resend out on every request, we just say 15, right? And that references that thing. So in practice, it basically gets us the same performance benefits as gzip in terms of the actual compression ratio. It's slightly less, but not significantly so. And it allows us to pick and choose which headers may be compressed. So in fact, you can transmit uncompressed headers, which addresses some of the security issues. Specifically, attacks against the compression context. So this is part of HTTP2. This is how headers are transmitted on the wire. So at this point, performance, right? Like, this is all great. Can you show me some numbers? These are numbers from our own Google products. So this is between our Google servers across a couple of different products. These numbers were actually captured with SPDY, but this was done, I believe, in November of last year, which is to say this SPDY version is very, very similar, almost identical to the latest HTTP draft. So these are basically one-to-one. And you can see that the actual performance benefits in terms of latency are variable. And that's to be expected because it depends on how your application is implemented, right? If you're doing things like aggressive sharding and using many connections, then you're going to get less benefit than maybe some other site that has more modular resources. So these numbers vary, but these are typically kind of the numbers that we see, somewhere in the neighborhood of 20, 30. If your app is particularly latency limited, we see benefits of up to like 50%. Which is quite nice, right? If you think about it, the only thing we've done is we swapped the transport layer. This did not require any changes at the application itself, which is like a free win as far as everybody's concerned. Similar numbers from Twitter. So in their case, these numbers are not for twitter.com. This is specifically for their API traffic. So this is the app that you run on your mobile device and their servers. They're using SPDY, and they're actually using SPDY and HTTP2, I should say, sorry. They're using HTTP2 internally as their RPC mechanism. That's actually one of the great benefits of HTTP2. Now that we reduce the overhead of metadata and we have all this framing, you can actually rip out a lot of the previously required RPC mechanisms which I think every large company in the Valley has implemented some variant of, because we all realized at one point that HTTP is not performant enough. And for example, Twitter has now adopted HTTP2 as the base protocol for all communication, both inside and outside the company, and they're having great success with it. And you can see kind of similar wins here. And perhaps one of the somewhat unexpected outliers is that we see some of the largest wins on the tail of the distribution, which is to say that the users that are really latency bound, like emerging markets and in other cases, are really benefiting the most. Which is somewhat counterintuitive, because one of the concerns with HTTP2 has been, hey, you're using only one TCP connection. And if you drop a packet in that one TCP connection, the entire congestion window gets reset, and kind of you get all these kind of negative things happening. But it turns out that there's other things that go in our favor, because we're pushing so much data through the single TCP pipe, we get faster retransmits, we get better performance out of TCP in general. So in practice, those things seem to cancel out, and we still get better performance. But that's not to say that we can do better than what TCP provides today. So another interesting study that came out, this is also speedy, but you can substitute HTTP2 in here. This was done by a couple of guys that were working on the implementation in Apache. And they ran a simulated workload, basically took a couple of different websites and ran a simulated workload against a server that uses HTTP1 and uses HTTP2. And they found that HTTP2 consumes far fewer resources, less memory, and all these things should be expected because there are just, frankly, much fewer connections, right? So you don't have to maintain as many sockets in all the rest. And if your architecture in particular is requests per process, then that really adds up very, very quickly. And in particular, this was important for TLS. And we're kind of getting to the end here. I did not talk about TLS in this talk because it's not critical to HTTP2, but that said, you will actually need it to deploy HTTP2. And you will need it for perhaps a somewhat unexpected reason. When we first started experimenting with SPDY at Google, we started running SPDY over port 80, just unencrypted. And we found that roughly 20 to 30% of our connections were just being dropped. We could not figure out why the TCP connection would just die. Sometimes we would get a reset, sometimes we would just get nothing. And obviously, if you're building a browser and having a 20 to 30% TCP failure rate is not acceptable, right? That's a pretty terrible user experience. So we put that same protocol over HTTPS, and lo and behold, everything's working fine. There's no longer any of these issues. And in fact, this was a similar finding that the WebSocket community found earlier, where they defined this new protocol, they tried to run it over port 80, and they found that there's just lots of, for no particular reason, the connection just dies. And the theory and hypothesis, and I think we've proven it, is that there's just a lot of middleware on port 80 deployed throughout the web that expects HTTP-like things, HTTP 1.1-like things. And the moment they sense something that is not like that, they either choke on it and die, or they intentionally close the connection and they don't tell us, and there's all these problems. And in fact, even client software, so antivirus software running on the user's device will intercept port 80 because they want to detect malware and do other things. And the moment they see something that doesn't smell like HTTP 1.1, they say like, "Ooh, this must be bad. I don't understand what it is. Let me just close the connection because I need to protect the user." So in practice, you actually need TLS. You need that end-to-end tunnel between the client and the server to guarantee that nobody in the middle will meddle with your traffic. So because of that, you need TLS in practice. And Chrome, Firefox, IE, Safari, everybody, all the clients have said that we will only implement HTTP2 over TLS, in the sense that we will only talk HTTP2 when we open a TLS connection, because otherwise we run the risk of our connection just being dropped, and that's a terrible user experience. We can't afford that. That's not to say that you cannot run HTTP2 over an unencrypted link. If you have your own controlled environment, fine. Please do so. Although even in a controlled environment, I would argue, let's say in a data center, you should still be encrypting your end-to-end links. We've had many different interesting findings come out in the last couple of years about data center traffic being intercepted. So you should encrypt your data center traffic and should have secure connections. But in practice, to talk to a browser, you need TLS. And TLS is a whole other topic that we can spend many, many hours on. I'll just say that it's mostly an unoptimized frontier, in the sense that many stacks are not tuned well. Like we can deploy TLS, but we can't deploy it well in many cases. And I'm talking about open source software and commercial software, which is just not leveraging a lot of the performance features. It is in fact possible to deploy one RTT handshakes with TLS. You don't have to incur 2 round trips. There's a variety of different optimizations that you need to hit in order to trigger that. But if you can do that, you can get away with one extra RTT. And there's other things that you need to be aware of, like things like revalidation or validation of certificates that may put a huge performance penalty on you if you don't get right. So if you're deploying TLS, or if you've deployed TLS, I really encourage you to kind of dive into this topic and understand how your stack is performing. And here's just one example. This is a matrix that I keep of the different support for different features, TLS features, in some of the most popular open source and commercial applications that you can get today. And as you can see, there's quite a bit of red. So like Apache Traffic Server is perhaps one of the few that gets everything right. But even there, you have to know what to configure and configure it correctly for the stuff to work well. So if you're interested in this sort of thing, I actually keep a site, which is istlsfastyet.com. And I'll spoil it, and I'll say, yes, it is. You just need to get some of the things right. And on that site, you'll actually find this table with links to all the appropriate resources. And I also keep a similar table for vendors, so CDNs. And one would hope that CDNs, whose entire purpose in life is to make things fast, would have figured this stuff out and made everything super fast. It turns out that's not the case in many cases, so you should do your due diligence and make sure that the CDN that you're using is in fact, has enabled all these features. And if not, please bug them, because from having talked to many of the product managers of those products, they tell me that having customers complain to them is the most effective way to get stuff fixed in an engineering org. Yeah, so we're actually at the end, so I just want to say that HTTP2 is here. Like it is here in the sense that it is deployed, it is widely available on the clients. The server support is rapidly evolving at this point. All of the popular servers that you guys are probably using have already implemented it or are implementing it right now. So maybe you don't want to be on the bleeding edge, but you should definitely start playing with this stuff. And if you're interested to check, or if you want to play with this stuff, I highly recommend actually going to this wiki page on GitHub. It contains a list of all of the implementations that we know of, at least in the HTTP working group, across all the different languages. So language bindings, servers, and other things. So you can plug that in and play with it. Okay, so finally, if you want to see the slides, they're available at this link here. And then I do have actually so I wrote a book with O'Reilly called High Performance Browser Networking, and I have a whole chapter on HTTP2. So if you want to dive in kind of deeper to understand the protocol, the framing layer, and other stuff, that's a great resource. It's free, you can read it online, or you can get a free PDF. So yeah, thank you.
So I'm curious, and have actually only the vaguest notion of the stuff that happens that can happen between the browser and the server, CDNs and proxy servers and things. Don't they sometimes need to see the headers and respond to them?
The question is, there are intermediaries that need to see the metadata, the headers and other things. And the answer is yeah, absolutely. And in that case, they need to terminate the connection. Terminate the TLS, the secure context. So you need to move your certificate down to there, and then if you need another hop to your origin, that hop also needs to be secure as well. So practically speaking, if you need to deploy, say, TLS with your CDN needs to terminate it. And there are actually other performance benefits for why you would want to do that, because you get a faster round-trip handshake with your CDN, but it does mean that you need to have your cert live at that layer.
So any types of supporting server initiated push update?
Sorry, can you say that again?
Server initiated push.
Server
similar to TCP, you have full duplex. You can
right.
Initiate.
Is there something in particular about push that you're curious about?
Yeah, server initiate. I want to initiate the push.
Oh, I see. So how does that actually work? So how do you deploy server push? Great question. Right now, there's a couple of patterns that are emerging. One is, once again, if you have full control over the server, your application can, if it's able to talk down to the server at that layer, you can say, initiate push. And here's the API for doing that. That's one way. Another way that's emerging where you have the reverse proxy is you actually use a different HTTP mechanism. So for example, one of the two interesting servers that you can play with today are NG HTTP and H2O. They use an HTTP header mechanism where your backend emits a response and it adds an extra header that says preload link rel preload URL. And what that header is effectively communicating to the proxy, it says, hey, I want you, the server, to preload this URL in the sense that I want you to initiate push on my behalf via this resource. So the server gets that header, it looks at that URL, says, okay, fine, I'll go fetch it and start initiate push to the client. So this is a standard header that is now being, this is the header that we use at Google, within Google, where our own products will emit that header and will trigger that. So that's one way, one of the strategies. Right. So that's a fantastic question. So just to repeat the question, HTTP2 provides a mechanism to express kind of priorities of different resources. We, the browser, have built in some rules around declaring what priorities are. What about the application itself? Why can't I have a web page that says, you typically classify images as low priority, but it just so happens that this image is critical to me because it's my hero image, it's like my splash page on my site, so I want it to be very high priority. And the short answer is today, no, there isn't anything. Are we talking about it in the standards working groups? Yes, absolutely. Right. So now that we have this mechanism, we're actually trying to figure out how do we expose these primitives, the weights and dependencies, and prioritization up to the client. So I expect that to come, but as of today, you don't really have anything, which is unfortunate. And I know that this is a very painful topic to many developers because we build in these rules into the browser and we keep changing them. So one day you optimize your site for one pattern, then we change it, and then it's like, what happened? My page was fast, now it's slow. So I'm hoping that we will change that in the future. So the question is about the kind of the layering, the network layering. What are we doing with HTTP2? Are we using TCP and other things? And short answer is we're using TCP. All we're doing is we took HTTP and instead of sending the plain text, we just added a framing protocol over it. And we're using TCP under the hood to guarantee all the other things, as it previously did. Now, it just so happens that when we first ran these experiments with SPDY and other things, we knew that TCP has certain behaviors that would become problems eventually, right? As with any performance problem, the moment you fix one bottleneck, you discover the next one. So we knew that TCP is going to be a bottleneck, but we knew that if we tried to solve both at the same time, the transport layer and the application layer, we would try to bite off too much. So we focused on HTTP2, which is just let's add the appropriate framing into application layer, and we'll use TCP. Later, and we're working on this now, we actually just published, if you're interested in this, an informational RFC. We started working on QUIC, kind of a fun acronym, which is effectively HTTP2 over UDP.
Yeah.
And
because it sounds like you have a lot of new flow control ideas.
Right. And we discovered in practice, we're able to control, in some cases, both the server and the client. We have our Google servers, we have our Chrome browser, and we can deploy TCP improvements, but deploying TCP improvements takes decades, right? I've been fortunate to share working space with somebody who works on the actual kernel and TCP implementation, and he submitted many patches 6 years ago, which have landed a long time ago, but are still in the pipeline for being deployed. So it's basically impossible to nudge the stack for many good reasons. So because of that, we started experimenting with UDP, where we were actually shipping the entire stack in the browser, which allows us to rev it very rapidly, which may sound crazy, and it's totally crazy when I first heard about it, but it turns out it actually works.
Yeah, that's what I thought you were going to do.
Right. So if you're interested in this, there is an RFC now published called QUIC, on QUIC, which is HTTP2 over UDP. And our intent is to take that to ITF and start talking about it. Maybe that is the HTTP3. I don't know. I'm not sure yet.
Is that in the context of the transport working group?
That's an interesting question. We don't know yet, right? Both groups are involved.
Okay. So you're running the application area right now?
Yes, I think so. Yeah.
Okay.
What about, in terms of nasty flow control, and your tests are, assuming there's unlimited bandwidth, how does this work, over carrier network and flow control?
Right. So turns out that TLS helps quite a bit. right? Because that obscures a lot of this traffic from proxies that meddle with this kind of stuff. That said, in practice, we know that there are issues with running with TCP and having just one connection, but looking at kind of the full performance profile of all the users that are using this stuff and have been using this stuff, we still see a significant performance benefit, even despite some of the edge cases and outliers. So there's been a long discussion in HTTP working group for like, should we really mandate or require that you only use one TCP connection? Like maybe we want to relax that. And the guidance so far at least has been to stick with one because the moment you go to two, you start losing a lot of performance benefits. Like now you have multiple compression contexts, so your compression is not as efficient. You can't prioritize as effectively over multiple connections. So you start forfeiting a lot of the things that we fought really hard to win. And yes, there are issues, but maybe the better route is to actually go to UDP, right?
Do you have any products, that are actually recognizing whether it's HTTP inside the TLS? I mean, it's a different traffic pattern.
Yeah, so you can actually detect. So the way HTTP2 is negotiated is there's an extension to the TLS protocol, which is the ALPN extension, which during the handshake advertises, the client advertises which protocols it supports. And the server confirms saying, like, we're going to use H2, right? Or we're going to use something else. So you as a proxy can actually observe that because the initial client hello is transmitted unencrypted. So if you're a proxy and you want to do something smart or not so smart about kind of flow control and other things, you could. So you could actually infer that like this flow is using HTTP2. I'm not aware of anybody doing anything good or bad with that yet, and I'm hoping they will not do anything bad.